Hello friends, in the previous lecture when we met, we considered different types of criterion. We focused on two different types of yield criterion. So the need for this yield criterion is, unlike experimental setting wherein we often impose a uniaxial tensile loading, in an actual application the mechanical condition experienced by the material is quite complicated. Often the loading direction are inclined, and we rarely expect a uniaxial or a biaxial loading condition. So therefore, in order to describe a point beyond which there could be a macroscopic plastic deformation in an application, we considered the different yield criteria, the two different yield criteria. So one criteria we refer to as the Oneness criteria, the other criteria we refer to as the Trescas criteria. Now the motivation behind both these criteria is that we need to consider all the components of stresses that is imposed in an application. So both these criteria, they play a significant role when we want to understand the behavior of the material, the mechanical behavior of the material in an application. So what Oneness criteria does is, the Oneness criteria, it considers all the different components of the stresses that a material experiences under the most complicated case. And all the components of stress, it splits into two. One is the stress that causes the plastic deformation and the stress that causes the elastic deformation. And from that, we identify the nature of the stress that causes the plastic deformation alone. So what essentially the foundation for both Oneness and Trescas criteria, the foundation for both these criteria is we identify the stress that is responsible for the plastic deformation. And when you look closely, the stress that is responsible for plastic deformation, the diagonal elements of the stress. So the stress, of course, is expressed as a matrix, because we need to consider all the components of stresses. It is expressed as a matrix, and this is stress that causes the plastic deformation. The diagonal element of this stress, it is rather compromised, but the non-diagonal elements, they remain the same. They principally remain the same. So it means the plastic deformation, the stress that contributes to the plastic deformation, is rather principally governed by the shear components. So therefore, the Trescas criteria, instead of considering all the components like the Oneness criteria, the Trescas criterion exclusively considers the shear components, and that too, it considers the maximum of the shear components. So supposing if you have introduced a stress of say sigma 1, sigma 2 and sigma 3, the maximum shear components is the difference between these two, that is sigma 1 minus sigma 2, sigma 2 minus sigma 3 and sigma 3 minus sigma 1. So of these pairwise combination of the different stresses that we have imposed, the Trescas criterion, it considers which one is the maximum. So there is a prefix 1 by 2 associated with each of these differences. So the Trescas criterion considers maximum of these three combinations, and whichever combination of the stresses gives you the maximum, it relates it to the yield point of your material and thereby establishing a criterion. So both these criteria stems from differentiating the stress that causes the plastic deformation from the stress that is exclusively responsible for the elastic deformation. While Oneness criteria considers all the components of the stress that causes the plastic deformation, the Trescas criteria, it qualitatively observes the nature of the stress and then relates it to the maximum shear condition. And that's the reason why the Trescas criteria is also referred to as the maximum shear criteria. So Trescas criteria, it studies the matrix that is responsible, the stress matrix that is responsible for plastic deformation, and it brings about a simplistic criteria, but the Oneness is more rigorous. It involves all the components. Now, towards the end of the previous lecture, we considered the fixing, or we considered a specific material, or when we consider specific material, what we are assuming is that the yield point of that material, we are assuming that the yield point is constant, and we have considered this yield point, or the stress that is, or the stress associated with the yield point, we are imposing using biaxial loading condition, and it means that we are imposing biaxial loading condition to a material, and this biaxial loading condition, it is equivalent to that of the yield point of the material. So this is the condition that we consider towards the end of our lecture. And when we considered such a condition, and when we related to the Trescas and the Oneness criterion, we were able to relate. So this will be the expression for the Trescas criterion, and it is possible for us to have a similar expression for the Oneness criterion. So in both these cases, what we are essentially doing is we are playing around with the biaxial loading that we are imposing, the biaxial load that we are imposing, the biaxial tensile load we are imposing, in such a way that both these loads, they contribute to, or they are equivalent to the yield point of the material. So we are varying the biaxial loads that we are imposing in such a way that both the combination of these two loads, according to Tresca separately and Oneness separately, they lead to the yield point of the material. And when we do that, what we end up having is the locus of the yield point. So when we say we fix the yield point, what we mean by that is we are considering a specific material with a specific yield point. And now we are playing around with the biaxial tensile loading according to Oneness criteria and Tresca criteria, in such a way that the yield point is ultimately achieved. And when we do that, we arrive at the locus of the yield point, and there is a specific shape associated with each of these criteria. So this is what we saw in our previous lecture. Now, the foundation for all these structures, or foundation for all these different criteria, it stems from the reason we need to have Oneness and Tresca criteria, and the reason we are able to relate it to this point is because we have. So this point is because we are considering a specific category of materials, and this specific category of material, they exhibit the mechanical condition, the mechanical behavior that they exhibit can be represented in this manner. And whenever we have considered, so in this we consider the mechanical condition, and in this axis we consider the response, and whenever we consider such a representation of the mechanical behavior, we always qualify it stating that this is rather the representation of a category of materials, that is metals and alloys. So this behavior is principally exhibited by, or it's largely exhibited by, the metals and alloys. Now let us, when you consider qualitatively the response offered by the material, this qualitatively the response offered by the material can be categorized as the irreversible change and the reversible change. When you consider qualitatively the response offered by the material, it can be categorized as irreversible and reversible. The irreversible are what we refer to as the plastic deformation, and the reversible are what we refer to as the elastic deformation. This response of the material is an effect of the mechanical condition that we impose, and that's the reason why we call it as response. Now we saw that the mechanical condition that we impose, it varies with the orientation of the plane, and even within the plane, but along a particular direction, the mechanical condition that we impose varies. So what we essentially have found out is, when we consider a system macroscopically, so if you consider a metal and its macroscopic state, and there is a loading direction that is pointing along the arrow, the stress experienced by this plane is much different from the stress experienced by this plane. The stress experienced by the black plane is much different from the stress experienced by the red plane. And moreover, even within the red plane, the stress along this direction will be different from the stress along this direction. So this is something that we have looked into, and this is what we refer to as the different components of stress. So macroscopically, the stress experienced by the material, the mechanical condition experienced by the material, it varies with the orientation of the plane, and even within the plane along the direction, the mechanical condition experienced by the material would vary. Now, when we want to quantify, so only when we are able to quantify these mechanical condition experienced by the material along a specific direction and along a specific plane, only then we will be able to describe it to the, or only then we will be able to understand the corresponding response. So only when we are able to understand the mechanical condition along a specific direction and along a specific plane, only then you will be able to describe the response of the material. Only then you will be able to either derive or discuss the response of the material. Again, depending on the orientation of the plane and the direction, the mechanical condition, the stress would vary, and depending on these differences, the response offered by the material would vary. Now, when you consider this macroscopic representation, such a representation, when you consider your material in the macroscopic scale as it is, like the ones that we see in our naked eye, in order to describe the difference in the mechanical condition experienced by the material with respect to a given plane and with respect to a given direction, we consider a specific coordinate system, a Cartesian coordinate system that involved x, y and z. So whenever we want to differentiate, whenever we want to describe the mechanical condition that is experienced by a specific plane along a specific direction, we made use of the Cartesian coordinate system. We made use of the frames of references. This is for the macroscopic consideration. Even when you consider, when you zoom in closely, and even when you look into the microscopic scale, even in the microscopic scale, if we want to describe the stress experience even on the range of 10 to the power minus 6 meters, even then when you want to describe the mechanical condition that is experienced by a given plane and a given direction, even there we need to make use of these coordinate systems. Now, but when you move even closely and when you zoom in and reach the atomistic scale provides us a different way of describing the plane and the direction. So let me repeat, when you start from the macroscopic scale, you need Cartesian coordinates to describe the plane and the direction. Even in the microscopic scale, in most instances we need, because in the microscopic scale is in the range of 10 to the power minus 6, even in there you need rather the Cartesian systems to describe the, in most instances you need the Cartesian coordinate system to describe the plane and the direction. However, when you move closely, when you zoom in closely and reach the atomistic scale, in the atomistic scale there is rather a more precise way of describing a given plane and the corresponding direction. Again, the need for describing the plane and the direction is because the mechanical condition, depending on the orientation of your plane and the specific direction that we are considering, would vary, and correspondingly the behavior or the response of the material would vary. So therefore it is required of us to dissociate or identify a specific plane and a specific direction in macroscopic scale, and at times in microscopic scale as well we need the coordinate system. But in case of atomistic scale, we have a unique way of describing the plane and the direction, and this unique way is possible largely in the systems that we are considering. This unique way of representing the plane and the direction at the atomistic scale is possible because of the nature of the system that we are considering. And here the nature of the system that we are considering is metals and alloy. The nature of the system that allows us to describe the plane and the direction in a unique way, particularly in the atomistic scale, is the atomic arrangements. So the characterizing feature, the unifying feature of metals and alloys is that they are crystalline in nature. Crystalline in nature because of their crystalline arrangement, the way they are, because of their crystalline nature. The property exhibited by metals and alloys are significantly different from the other category of materials. And when you consider what is this crystalline arrangement means, so this crystalline arrangement are nothing but they stem from the atomic arrangements. So the crystallinity of the metals and alloys, they stems from the atomic arrangements. And when you have a long range arrangement of atoms, a long range regular arrangement of the atoms, it ultimately leads to the crystalline material. So what crystalline material principally possesses is, it possesses the long range regular arrangement of the atoms. So we also have minerals which are crystalline in nature, and in our case we are focusing on the metals and alloys, and these metals and alloys are crystalline in nature because they have long range arrangement of the atoms. Now long range, rather it could be translated to be, or it could be considered to be a subjective as a subjective term, but in the case of describing the crystalline nature of the material, there is a specific value associated with the long range arrangement. So when your long range arrangement is of the order of 10 to the power 4, so you have rather an arrangement of the atom locally in the atomistic scale, and this arrangement of the atoms, when it extends to the range of 10 to the power 4, then such an arrangement we refer to as the crystalline arrangement. Again, when you have a local regular arrangement of the atom in the atomistic range, that will be referred to as the short range arrangement of the atoms. It is possible for a material to have a short range arrangement of the atoms where the atoms are locally arranged in a regular manner. This can only be referred to as the long range arrangement when this local regular arrangement is extended to the order of 10 to the power 4. So the long range is not a subjective or it's not a qualitative term, it has a quantitative aspect to it, and that quantitative aspect comes from this value, that is 10 to the power 4. Now the long range, owing to the long range arrangement of the atoms. So in addition to being the long range arrangement of atoms, in metals and alloys, what we also observe is these atoms are regularly arranged. In addition to being exhibiting a long range arrangement, they are also regularly arranged. The atoms and the ions in the metals and alloys, they exhibit a combination of both long range and regular arrangement. Now it is possible for us to represent, owing to this long range and the regular arrangement, particularly owing to the long range arrangement, or rather the regular arrangement, it is possible for us to represent the crystalline material using, or in a 3-dimensional setup, using what we refer to as the unit cell. So that the arrangement of the atoms, since they are long range and also they are regular, it is possible for us to represent a given crystalline material using what we refer to as the unit cell. So we have considered that it is also possible for us to represent it using in 2 dimensions, that we refer to as mass. But in case of the metals and alloys, it is possible for us to represent the crystalline arrangement of the atoms in a metal and alloy using the 3-dimensional representation called as the unit cell. Now what essentially the unit cell comprises of it is this unit cell. Again, it indicates, it represents the long range regular arrangement of the atoms, and it has a specific shape associated with it, it has a specific morphology associated with it, and in addition to that, it describes the possible positions of the atoms. So the unit cell, what it essentially encompasses, what essentially the unit cell describes it, is the unit cell, it indicates a specific morphology, or it indicates it is of a specific shape, or it is of a specific morphology. Secondly, the unit cell, it shows the possible positions of the atoms. Now when you consider the shape, when you want to describe the shape of the unit cell, there are different ways of describing the shape of an unit cell. Now depending on the shape of the unit cell, the position of the atoms will vary, and correspondingly the overall arrangement of the atoms would vary. Now unit cell, representation of the long range regular arrangement of the atom, and this unit cell, it is described by 2 features. One is the shape, and then the other is the possible position of the atoms. Now when you consider the shape of the unit cell, we will be able to describe the shape of the unit cell only when we are able to describe the unit cell using certain parameters. So we need to have certain parameters, we need to describe certain parameters, only then we will be able to describe the shape of the unit cell. Only then we will be able to associate a shape to the unit cell, and this unit cell, only then we will be able to relate it to the atomic arrangement. So in order to do that, when you consider the framework of the unit cell, it is based on, or it can be represented in this manner, where the sides of the unit cell are associated with, again, the frame of references that we are familiar with. And once we are able to associate the unit cell with the frame of references, it enables us to rather describe the unit cell in itself. So what we now want to have is, we want to have parameters, we want to derive parameters that enables us to describe the morphology of the unit cell. So once we are able to describe the morphology of the unit cell, and then we will be able to position the different atoms, and once we are able to do both these, then a unit cell will represent a given material. So start with, we need to have a morphology of a unit cell. Again, since we have the regular arrangement of the atoms, the unit cell can be of the form, it can be either of the form of a 3-dimensional cube, or it can be of a cuboid. So there are 2 possibilities, it can be as a cube or it can be as a cuboid. Again, this is principally because we are considering regular arrangement of the atom. So therefore there are 2 possibilities of the unit cell, cube or a cuboid. Now the difference comes from the dimensions, and in order to introduce this dimension, we are considering these coordinate systems. So only here we are considering the coordinate system. Apart from that, just to introduce these parameters that describe the unit cell, we introduce this coordinate system. Apart from that, whenever we are describing anything within the unit cell, we will no longer need the coordinate system, and that is one rather advantage of considering the behavior of materials in the atomistic scale. We no longer need the frames of reference, and we can describe the plane and the the direction using the parameters of the unit cell. And that is the one advantage of considering the atomistic scale description of the mechanical behavior. Now, we have introduced this frame of reference. We have superimposed this frame of reference onto the unit cell, and the unit cell can be cube or cuboid again because we are considering the regular arrangement alone. The unit cell, it represents the regular arrangement alone. Now, in order to discuss the shape, we need parameters, and one of these parameters are the length-wise parameters or the length scale parameters along this coordinate system. So, these parameters are along the coordinate axis, and these can be referred to as A, B and C. So, when you consider a unit cell and you superimpose the coordinate system that we are familiar with, the Cartesian coordinate system we are familiar with, we are able to come up with 3 parameters to describe the morphology of the unit cell. In addition to that, it is possible for us to have an angular parameter, and this angular parameter will also, we also need this angular parameter. This angular parameter also plays a critical role rather in describing the morphology of the unit cell. So, we need to describe the morphology of the unit cell, we need 2 parameters. One is a length scale parameter, the other is the angular parameter. The length scale parameters are referred to as A, B and C. The angular parameters are referred to as the alpha or rather alpha, beta and gamma. So, we have combination of length scale parameters and angular parameters to describe the shape of the unit cell. Now, when you consider the different possibilities, so we have length scale parameters and angular parameters. So, there are different possibilities that we can associate, we can attribute to these parameters. All these can be equal, all the sides can be equal, all the lengthwise parameters can be equal, all the angular parameters can be equal, one can be different, so on and so forth. But when you consider the metals that are of huge relevance to us, the metals that are of highly used in application, highly applicable materials, often these highly applicable material, they fall under what we refer to as the cubic crystal structure. They exhibit a cubic crystal structure. Okay? The materials, the metals and alloys that we largely use in an application, they follow cubic crystal structure, and at times they also can be hexagonal. They can exhibit hexagonal close packed crystal structure. So, even though there are several possible regular arrangement of the atoms, so based on the combination of the length scale parameters and the angular parameters, we can build several crystal systems. Even though there are several crystal systems that are possible, when you consider the metals and alloys that are huge relevance to us, often they fall under the category of cubic crystal structures or cubic crystal system or hexagonal crystal system, or they will fall under the category of cubic crystal structures or hexagonal close packed crystal structures. Now, when you consider the cubic crystal structures or cubic crystal systems, the morphology of the cubic crystal systems are rather characterized by the equivalent nature of the lengthwise parameter and the equivalent nature of the angular parameter, which is rather equal to 90 degrees. So, the characterizing factor of the different unit cell that fall under the category of cubic crystal system, the characterizing feature is they have the lengthwise parameter, the magnitude of the length of each of these lengthwise parameters, they are equal, and the angle between these lengthwise parameters is 90 degree, and this is what describes the cubic unit cell. Now, before moving on to the hexagonally close packed crystal structures, let us consider the cubic unit cell first, and using the cubic unit cell, we will describe the positions of the atom. We will see how one can describe the position of the atom in a unit cell that is of or that represents the cubic crystal system. Again, the reason we are focusing on the cubic crystal system is because it is highly relevant to us. It is also possible that the desired properties is rendered by the the materials with cubic crystal system, or it is that reason why we have these specific category of materials which are highly applicable to us, because the property that we desire is often rendered by the material with cubic crystal structures. And since they are hugely relevant to us, we are starting off our discussion with this category of materials. Now again, what once we have considered or restricted ourselves to the cubic crystal system, then the shape, one of the factors that describes the shape, one of the factors that describe is now fixed, because the magnitude of the lengthwise parameters are equal, and correspondingly the angle between them is 90 degrees. So should now the unit cell, the shape of the unit cell, one feature of the unit cell is now fixed. Now we are then required to describe the other feature, that is the possible positions of the atom. So when you consider the possible positions of the atom in a cubic unit cell, so let us first represent a cubic unit cell. The cubic unit cell, the lengthwise dimension of the unit cell is identical. So therefore the unit cell, when you consider the shape, it's in the form of a cube. Now when I want to talk about the positions of the atoms, to complete a unit cell, I need to know the positions of the atoms. When I want to talk about the positions of the atoms, I need to know how to describe each of these points in this unit cell. So we have, initially we will do it, when we don't have this unit cell, we will do it using the Cartesian coordinate system. But now we are talking in context of the unit cell, we need to know how to describe a point within this unit cell. And since we already know that all the sides are of equal size in the cubic crystal structures, so all these lengthwise parameters are identical and they are equal to A. Now any point within this unit cell can be described using this characteristic parameter, this characteristic lengthwise parameter. So initially when you want to describe any point in the unit cell, you would use the Cartesian coordinates, but now any point within the unit cell is rather described based on these lengthwise parameters. Now when I want to describe this point here, so this point, even though it is along the y-axis, now the dimension or the magnitude along the y-axis is represented by A. So then this point is just, it lies along the y-axis, and therefore there are no x and y z contributions. So therefore this point is represented by 0, A, 0. And the same way it is possible for us to describe any point. This point here, if you consider, this point is, it can be represented by A by 2, and 0. So if you consider this point, it can be represented by A by 2, 0, even though it is implicitly assumed that there is x, y and z coordinates associated with the unit cell, but the way we describe the point is based on the parameter, this parameter which we refer to as the lattice parameter. We describe the point within the unit cell, or on the unit cell using A, and that point using the parameters that is associated with the unit cell, no longer based on x, y and z. Even though it is implicitly assumed that one of these axes they have, or we have superimposed the x and y coordinate system, x, y, z coordinate system on the unit cell, we will soon realize that even independent of this x, y, z coordinate system, it will be able for us to describe a point and several parameters within the unit cell. Nevertheless, what is made possible for us to do within a unit cell for a cubic crystal structure is we are able to describe a point on and within the cubic unit cell using the lengthwise parameters of the unit cell. Now, based on, once we are able to describe the positions or points on the unit cell and within the unit cell, then we will be able to position the atoms on each of these points, thereby giving us different crystal structures. So depending on the crystal structure, the positions of the atoms in the unit cell would vary, and in which point or in which positions would the atom occupy is now described by using the lengthwise parameters associated with the unit cell, not x, y and z. Now when you consider the other rather descriptions, or if you have to describe if you have to focus more on the unit cell, particularly when we want to consider the unit cell in relevance or in reference to that of the mechanical behavior, the other parameter that we should be able to describe is plane and direction. So in order to describe a unit cell, we need morphology and we need positions of the atoms. So we were able to describe the morphology based on the crystal system. Since we have considered cubic crystal system, we were able to describe the morphology based on this characteristic feature. Now, once we have this feature, then it becomes possible for us to describe the point within an unit cell. So it becomes possible for us to describe the point within a unit cell once we are able to provide a morphology to the unit cell. And once we are able to describe the point within the unit cell, then it is possible for us to describe the position of the atoms within the unit cell. Now, once we are able to describe the position of the atom within the unit cell, then ultimately we have specific unit cell that represents a given material. So, depending on the nature of the arrangement of the atoms, you now have a representation of that particular arrangement in the form of the unit cell. For that you need morphology, and for that we need positions of the atoms. So we were able to describe by describing the points, we are able to now describe by introducing the way to describe the points. Now we are able to position the atoms and thereby establishing a real unit cell, that is reflective of a material. Now once we have built the unit cell that is reflective of a crystalline material, that is reflective of a metal or an alloy, now it becomes vital for us to describe the plane and direction within the unit cell. So using the way we have described the point in the unit cell, we should now be able to describe the plane and the direction. The reason we should be able to describe the plane and the direction is because depending on the plane and the direction, the mechanical condition will vary, and correspondingly the mechanical behavior will vary. So therefore it should be possible for us to describe the plane and the direction in the atomistic scale, that is much different from how we do it in the macroscopic scale. Now in order to do that, let us consider, again let us start off with the cubic crystal structure, and in this cubic crystal structure we attempt to describe the plane, a desired plane. Now let us assume that the one in the red is our desired plane. Now in order to describe this desired plane, there are three steps we need to do, or we need to take 3 steps. First step is to identify the intercept, the place where the desired red plane meets with the different axes. Again, even though we start off with the axis, we will soon realize that we will be able to arrive at an invariant way of representing, a way of representing the plane which is independent of the axis. Even though again we start off with representing or describing the plane with the axis, it is possible for us to arrive at a representation that is independent of the axis. Again, to start off in describing how a plane works, or how to describe a plane, we consider the desired plane and see where this particular plane meets with the axis, the frames of reference that we have considered. So when you consider this red plane, it is parallel to that of the y-axis. So it is possible for us to assume that this plane meets the x-axis at infinity. So the plane that we have considered in red, it is parallel to the x-axis. So it is possible for us to assume that this plane meets the x-axis at infinity. However, this plane meets the x-axis at a, which is the lengthwise dimension of our unit cell. So while the desired plane is parallel to x-axis, the desired plane intercepts with the y-axis at length a. So this length here is a. At a, the desired plane, it meets the y-axis, and similar to that of x-axis, the desired plane is parallel to that of the z-axis. So it can be assumed that it meets the z-axis at infinity. So what essentially in step 1 we have considered is, we have considered where the given plane, the plane of our interest, meets with our different coordinate systems, so different axes, and we have found that it is parallel to 2 of the axes. So therefore we have considered them, we have assumed that it meets these axes at infinity and it meets y-axis at a. Now the second step involves taking the reciprocal of this. So when you take the reciprocal of this, 1 by infinity, it will be 0, and this will also be 0, and finally this will be 1 by a. So what essentially we have done is taken the intercepts in the first step, taken the reciprocal in the second step, and what we do in the third step is we represent it using, rather we represent it in this manner, separated by a comma, and we enclose it using a bracket of this form. So we consider the intercepts, we consider where the plane meets with the different axes, and then we take the reciprocal of the point of contact, and then we express it using this parenthesis. And now what is ideally done is, this is rather factorized. We factorize this term here, meaning it is possible that we can multiply each of these terms with a. So ultimately, when you multiply each of these terms, all the terms with a, you will end up with 1, 0, 1, 0, and this is what represents the plane in red. So when you want to represent the plane in an unit cell, okay, what essentially we have to do is 3 steps. 1, find the place or point where the plane meets with the different axes. Then take the reciprocal of it, and finally normalize or factorize the different points that, or the different parameters that we have identified, and we have enclosed to represent the plane. So this is the representation of the plane. And here the nature of the bracket, here we have this bracket, the curved bracket, and it means that we are talking, so in the context of crystallography, in the context of when we are describing the plane in the atomistic scale, in this context, when your these values are rather enclosed by this form of bracket, they indicate plane. So generally, so depending on the values these parameters assume, they indicate a different plane. So generally they are represented as a variable, they are represented by h, k and l, and when the h, k and l, these are variables that represent that can assume different values within the bracket, and when they assume different values within the bracket, they indicate different planes, and these are referred to as the Miller indices. And Miller indices, when they are rather enclosed by a curved bracket, then what it represents is a plane. Now let us consider, before finishing off our discussion on the plane and how to describe them, let us consider a different plane now, and for that we will start off the representation of the cubic unit cell, and let us consider a bit more difficult plane to describe. And this plane is of the form here. So let us try to rather describe this plane. Now describing a plane is a 3-step process. The first step is to identify the points where the plane meets with the x, y and z axis. So it is x, y and z axis. Now this plane, it meets the x axis at A. It also meets, so it meets the x axis at A, it meets the y axis at A and the z axis at A. And now we have to take the second step would be to take the reciprocal of it. So it will be 1 by A, 1 by A and 1 by A. So x, y and z reciprocal. Now what we need to do is we have to place them in the parentheses, and we have to normalize it, and when we do that, this plane is now represented by 1, 1, 1 plane. Now let us consider, in the same framework, let us consider a different plane which is of this form. It meets the x-axis, so it meets the y-axis here, it meets the x-axis here, and it meets this point here. So let us consider a plane. So let us consider this plane here, the plane in blue. So we have already seen the plane in red. Now let us consider the ways to describe the plane in green rather. Now when you want to describe the plane in green, what becomes difficult is, it is rather, even though we are able to identify where this plane meets. For instance, when you want to describe the plane in green, this plane meets the x at A, this plane meets the y at A, but we don't know where this plane meets the z axis. Now our initial z axis is here, and we don't know where this plane meets the z axis. So what can be done is, it is possible for us to shift our origin from this point, from our original point. So this was our original origin, to this point here, to O prime. Then now when I shift my origin, what it enables us to do is, it enables us now to describe the point where the plane meets the z-axis, and that will again be A. So when I shift my point, now it becomes possible for me to describe where the plane meets the z-axis. However, with respect to this point, with respect to this origin, with respect to my new origin, so I have my x here, y here, with respect to my new origin, the point where the plane meets the x-axis is here. The point with respect to my new origin, the point where the plane meets my x-axis is here. The point where my plane meets the y-axis is here. So they are in the negative side of the quadrant. So originally, with respect to the original point or the origin point O, the plane met the x-axis at A and y at A. However, since it is difficult for me with respect to the original origin to describe where my plane meets the z-axis, I consider a new origin. With respect to this new origin, the plane meets the z-axis at A. However, it meets the x-axis at minus A and y-axis at minus A. So once I shift my origin, then the point where my plane meets the x and y axis also changes. So therefore, when now I am describing the green plane, I have to describe it completely based on the new origin. So therefore, these would be my point of contact minus A and A. If I take the reciprocal, it will be minus 1 by A, minus 1 by A and 1 by A. And if I normalize it, it will be minus 1 and 1. And ultimately, when the minus is associated with the Miller indices, it is represented by, instead of minus, a bar on the top. So 1 bar and 1. So this represents the plane in the green. So this represents the plane in green. So often when we want to describe a plane within a given unit cell, it might be required of us to shift the origin that is associated with the coordinate system. So when we do that, not only the points associated with the z and z axis would change, the points associated with other axes would also change. So therefore, when we want to describe the green plane, we have to shift our origin, and the resulting expression for the plane in green would be 1 bar 1 bar 1. So when it is not always that when we are describing a plane within a unit cell, we will fix our origin. We would have to shift our origin when we want to describe a plane within the unit cell. On top of it, when you consider the nature of the plane, the nature of the red and the green plane, what essentially they are doing is, what essentially is the characteristic feature of this plane, both these planes are, is that these planes are connecting rather three opposite corners of the unit cell. Both these planes, that is the red plane and the green plane, they are rather connecting the opposite corners of the unit cell. So when you consider geometrically, both these planes are equivalent. So both these green and the red planes are equivalent because they are connecting the points, that are completely opposite to one another in all the three directions. So both these are rather equivalent. So in other words, when you look even more closely, it is possible for us to change the x, y, z, to rename the x, y, z and change the point of origin in such a way that both these planes can be represented by the same Miller indices. I repeat, the red and the green planes, they are, when you consider geometrically, they are equivalent because they are connecting points of the unit cells that are completely opposite to each other in all the three directions. So geometrically they are equivalent. Secondly, it is possible for us, by appropriately changing the way we represent x, y and z and the position of the origin, using the same Miller indices to represent both these planes. So when you have a plane which are geometrically equivalent, and the same on these two different planes, when you have two different planes which are geometrically equivalent, and both these planes can be represented by the same Miller indices by appropriately choosing the origin and also by appropriately considering the x, y and z. Meaning, if I consider in this the frame of reference, that is the new frame of reference, that is the position at O prime, if I consider that my positive side of the y is along this direction and the positive side of x is along this direction, if I do that, then the green plane will be represented by 1, 1, 1, similar to that of the red plane. So what essentially we have done is, we have described when we are moving the origin from O to O prime, we have considered, we have rather rotated the frame of reference in such a way that the Miller indices 1, 1, 1, it indicates both the red plane and also it indicates both the red plane and also it indicates the green plane. So what essentially we have done is, using the same Miller indices, we have now described two different planes, and this is possible because we have shifted our origins, and we have shifted and we have played around with, we have rotated our frame of reference in such a way that using the same Miller indices, we are now in a position to describe two different planes. And again, these two different planes are equivalent, they are rather geometrically equivalent. Such planes are referred to as the family of planes, and these family of planes are rather enclosed by a flower bracket. So what is the characteristic feature of family of planes? The characteristic feature of family of planes is that these family of planes, they are geometrically equivalent, one. Secondly, by appropriately changing the origin and the way we describe the coordinate system, it is possible for us to describe different planes using the same Miller indices, and these are referred to as the family of planes. Now, when you consider the family of planes, when you consider all the planes that are equivalent to 1, 1, 1, for instance, this family of planes is rather invariant to the coordinate system. This representation of a plane as a family of plane is rather invariant to the coordinate system. However, in whatever way you consider your coordinate system, supposing instead of x, y and z, you consider this to be your x, this to be your x, this to be, or rather if you consider instead of this representation, if you consider this to be your x, this to be your y, and this to be your z, or if you consider the other direction to be your positive side of your x and the other direction to be your positive side of your y, and whatever combination you consider, the plane that is represented by any combination will fall under the family of planes. So whatever combination you give to the coordinate system, be it positive negative combination or the rotational combination, whatever combination you give to your coordinate system, the resulting plane, when you describe a given plane using different combination of the coordinate system, all will be rather captured by the family of plane. So the family of plane representation is invariant of the coordinate system. When you represent a plane, and along with plane, if you represent all the equivalent planes, then in the form of the family of planes, then what you are doing is you are expressing a plane that is invariant. You are expressing a plane in a way that is invariant of the coordinate system. So essentially we have now expressed a plane within the unit cell or a plane in the atomistic scale that is invariant of the coordinate system. We have gotten ourselves rid of the coordinate system that we impose, and we are now exclusively describing the plane based on the atomistic scale, based on the arrangement of atoms, based on the unit cell alone. So this family of plane, the way we described it, is exclusively based on the unit cell alone, and it is independent of the coordinate system, whatever nature of the coordinate system you consider. And in that coordinate system, if you consider, if you describe a plane, and when you represent the plane as a family of plane, all the combination of the coordinate system, be it change in the naming of the coordinate system or the change in the way we have considered the positive and negative coordinates, all of it will be encompassed in the family of planes. So with this, we will wind this lecture up, and in the subsequent lecture, we will start off with the direction and we will consider the other relevant units. Goodbye.